For this last video, we're just going to zero in on translations from natural language into quantified sentences of complex noun phrases, and then translations from those sentences in quantified FOL back into English. Now, we already saw in an earlier video that existentially quantified sentences are roughly equivalent with the English sentences in which the operative term is something like some or a or an. And in this video, we're just going to see how these things get translated by making use of our prior notion of a grammatical subject. For example, suppose we encounter the sentence, "Some happy student is on a break." Well, here we have this whole grammatical subject, which we can symbolize as there exists an X which is happy and a student. And then we can take this whole grammatical predicate and symbolize it as, we'll just use the predicate break X for X is taking a break. Now, with existential sentences, we don't have to separate out the grammatical subject and predicate like this, as I've done with the parentheses here and here. Because of the commutativity of and, this whole sentence without these parentheses is the same. But it's worth it just to see the subject separated out like this. And as we'll see in just a minute, we have to separate it out with parentheses for universally quantified sentences. Now let's turn to those now. Suppose, for example, we want to say that every happy student is taking a break. Now we've seen that the universal quantifier is roughly equivalent with our English determiner all, and so forth. So suppose that instead of some happy student is taking a break, we wanted to say every happy student is taking a break. We'll separate out the grammatical subject here, the way we did with the existentially quantified sentence above, and we'll write it as X is a student and X is happy. We'll add in our universal quantifier there. And then we'll take this second part and drop it in here. Now notice that this has to be a conditional sentence for reasons we discussed in the last video. So it looks like this. The key thing to recognize here is that this is our main connective, this conditional arrow right here. So what this says is that for every X, if it holds that X is a student and happy, then, main connective, X is on a break. So you can see that in order for this sentence to be well formed, we need to have the parentheses here and here. Otherwise, this sentence wouldn't be well formed at all. Now, sometimes it happens that the noun phrases that make up the grammatical subject are not as straightforwardly in the subject position as they are in this case right here. For example, we might have a sentence like, Alex owns every chestnut horse. Here we clearly have this quantificational term, every, which we know is our universal quantifier. But where does it go? We just have to think about the truth conditions of the sentence and what it's really saying, and then we'll see how to do this. The solution is to start with this whole phrase right here, and if you like, I'd encourage you to pause the video for a minute and think about how you might do this. The solution is to take this whole noun phrase here and treat it as our subject. We would say, for every X which is chestnut and a horse, if it's such, then Alex owns it. So we bring this down over here, and we put the whole thing in parentheses. And there you have it. One final remark, it doesn't matter much which order these two appear in, of course, because the and symbol is commutative, which is to say P and Q is equivalent with Q and P. So you could say for all X, horse X and chestnut X, it doesn't much matter. Now all this is pretty familiar stuff, but there are ways that the universal and existential quantifiers behave which looks a bit weird to us and seems quite unnatural, and here's those two ways. I said a minute ago that the existential quantifier behaves roughly like some. The problem is that in English we usually mean some but not all, and this is not equivalent with our existential quantifier. Our existential quantifier is exactly equivalent with at least one, as we've already seen. So it's perfectly consistent if you're faced with a world in which all dogs are mammals to say some dog is a mammal, even though in English what's conversationally implied is some but not all. There are reasons for this based in the semantics of natural language, which were developed by Grice in his notion of conversational implicature, which we saw in an earlier video. Basically, the idea is that you should make the strongest statement that you can on the basis of what you know. So if I said to you some, and what I meant was at least one, even though I knew that all, for instance, dogs are mammals, then I'm not making the strongest statement I can. And so our some in English and other natural languages has this additional sense of some but not all. It's a stronger some. But here again, the test for this is cancelability. You can say, for example, someone brought bread to the picnic, and in fact, everyone did. There's nothing contradictory about this sentence. And so the some but not all sense of some is not canceled by this added universal. And so it's not part of its semantics, but it is conversationally implied. With this in mind, we can be clear that when we encounter a sentence that says something like, there exists an x that's p, all that this is saying is that at least one x is p, not that some are and some aren't. So that's an important way in which the existential quantifier comes apart from the way that we use some in natural languages like English. As for the universal quantifier, we've already seen that it's roughly equivalent with the English all, except that we tend to use English all to mean all and there are indeed some. So we tend to use it in the sense of all, but with the implicit assumption that the things that we're talking about exist. The problem is that the sentence all s is p is properly symbolized in FOL as for all x, if x is s, then x is p. But let's just isolate this conditional for a minute and look at it in the context of a truth table. So it's perfectly fine if there are s's that are p, as it corresponds with our top row here. And if x is s but isn't p, then the sentence comes out false, and that seems right too. The problem is with these bottom two rows. Supposing that it's false that x is s, and so in either case the conditional comes out true. Accordingly, the things that are being discussed by a universally quantified sentence don't have to exist, and in fact if they don't exist, it comes out vacuously true. For example, all unicorns are aliens comes out true because whether or not there are aliens, there are no unicorns, and so the antecedent here is not satisfied, and so the whole conditional comes out true. Now, if this strikes you as weird, it's because it is, but if you think about the truth table for the conditional, you'll see why it holds. If we wanted to express that something wasn't a vacuous truth, we would just add an existential sentence onto it. So for instance, suppose I wanted to tell you that in our world, every cube is large, but I want to make it clear that there actually are cubes in this world, rather than that every cube is large comes out vacuously true simply because there are no cubes. What I would do then is write it out as follows. Every cube is large, that gets us that if something is a cube, then it's large, and I can add on to this at least one thing, something, is a cube. Here the main connective is the conjunction, and so these could appear in either order. So that's the way that you would express that a universal statement is not vacuously true if you wanted to make that clear. Nevertheless, when we encounter them on their own, universal statements can be vacuously true, and this is a very important thing to be aware of. And that wraps up week 11 and our introduction to the notion of quantification and the quantificational symbols. As ever, let me know if you have any questions.